Houston, Texas, high noon. The sun here doesn't just shine. It presses down on your shoulders like a heavy, hot blanket. The air above the scorching asphalt shimmers with heat waves, and your lungs fill with a thick, distinct smell. A mix of heated rubber, dry prairie, and diesel fuel. I'm standing at the gates of the Genan plant, the world's largest tire recycling facility, and I can feel the soles of my boots starting to soften on the blistering Texas ground. Today, I'm not just a tourist. I'm a witness to a massive technological alchemical process, where what the world considers waste that won't decompose gets transformed into energy, and the very foundation of the highways we drive on. Houston didn't just greet me with sunshine. It slammed me with a wall of sticky heat that folks down here in Texas call the devil's breath. But the second I stepped through the entrance to Genan's facility, the sounds of the city, distant highway hum and rustling wind, instantly shifted into something far harsher. Industrial chaos. But chaos that's perfectly ordered, rhythmic, almost primal. The first thing that hits you isn't the sound, it's the vibration. You don't just hear it. It rattles your chest like a low bass line at a rock concert. That's the giant motors firing up the heart of the plant. And spread out before me are the real black Himalayas. Thousands, maybe tens of thousands of used tires stacked into neat but staggering mountains. Everything's here. Thin wheels from compacts that only ever touched smooth asphalt, all the way up to massive donuts from mining dump trucks, treads tall as a person. They all came here to die, so they could be born again. The smell here is something else. It's not just the stench of rubber. It's a complex cocktail of heated polymer, traces of road tar baked into the treads, and hot metal. The Texas sun mercilessly scorches these black surfaces, and the heat radiating off them makes you feel like you're standing next to an open oven. The air between the mountains has solidified. It's thick and oily. I watch as another truck rolls up. The hydraulics groan as the bed lifts, and hundreds of tires tumble down with a muffled rumble. Thump, 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 cascading to the foot of the black mountain. This sound of rubber hitting rubber layers over that same endless vibration from the plant's engines. It creates this uncanny sensation of being inside a living organism. The plant breathes with this rhythm. It's hungry, and these mountains are its food. The vibration intensifies when the feed conveyors kick on. You see these massive manipulators, like the claws of prehistoric monsters, tearing into the piles, snatching their prey. In this place, on the edge between old junk and raw material, you feel tiny. We're following the conveyor belt that leads straight into the heart of the main floor. Here, that vibration I mentioned earlier transforms into physical force, pounding against your eardrums. We approach it, the primary shredder. If those mountains of tires were a graveyard, then this machine is the industrial meat grinder that knows no mercy. The first thing that hits you is the contrast between speed and power. You'd expect the shredder to spin at breakneck speed, flinging chunks of rubber in every direction like a blender. But no, the shredder's shafts move slowly, almost lazily. But within that slowness lies colossal torque, force capable of crushing stone. It's a deliberately engineered method. Low rotational speed prevents the rubber from overheating, keeping it from melting and sticking to the blades, which would turn the machine into a gummy trap. When the next tire, say, a massive wheel from a Texas pickup, hits the rollers, something happens that makes you flinch. The tire tries to hold its shape. Its steel belt, that same skeleton that carried tons of weight on the road, puts up one last fight. But hardened blades made from special alloy dig into the tread like the teeth of a prehistoric predator. 1 second, and you hear that distinctive crunch as the steel wires inside the rubber snap under hundreds of tons of pressure. In that moment, bright, angry showers of sparks fly out of the shredder's jaws. It's the friction of the steel belt against the blades, creating miniature lightning bolts inside the machine's dark belly. The heat here becomes almost unbearable. If it was just hot outside in Houston, near the shredder, the air heats up to a temperature where the sweat on your forehead instantly turns sticky with rubber dust. You can smell the frictional heat, sharp, metallic, with notes of burnt sulfur. It's the smell of matter being physically destroyed. Dust is everywhere here. It's not just floating in the air, it's dancing in the beams of industrial lights, settling on every surface like black velvet. These are tiny rubber particles released during the tearing process. You can see chunks falling from beneath the rollers onto the exit conveyor. This isn't a tire anymore. These are shapeless, torn scraps of rubber, roughly the size of an adult man's palm. Mangled strands of steel wire stick out from them, those same cord fangs that magnets will pull out in the next stage. The chunks of shredded rubber that just passed through the shredder's jaws move along on the conveyor belt. They look terrible, torn, dirty, hot, with those same mangled steel wire threads, cord fangs, sticking out from every black edge. Right now, one of the most cinematic stages at the Genan plant begins. We're approaching the magnetic separation zone. Above the conveyor, where chunks of tires race by in an endless stream, massive blocks hang suspended. Overhead electromagnetic separators. They hang low, almost touching the black flow, humming with voltage. What happens on the belt resembles an uprising of the dead. When a ragged chunk of rubber enters the magnet's zone, the steel threads inside it react instantly. You see it with your own eyes. Metal wire that a second ago was part of a solid framework suddenly comes alive. With savage force, it tears free from its rubber prison, dragging the entire chunk with it, or simply slipping out like a knife through butter. Metal literally shoots upward, defying gravity. It looks like strange, aggressive magic. Thousands of steel needles and twisted wires slam into the magnetic belt with a loud crash, spinning perpendicular to the main conveyor. This is that endless clacking, the sound of thousands of metal fragments hammering into the separator's steel armor. The heat in this zone is unique. The magnets consume a massive amount of electricity and generate heat themselves, mixing with the warmth from freshly cut rubber. You're standing in a cloud of a specific smell, a blend of ozone, which always accompanies powerful electromagnets, and warm, raw metal. It's the smell of a forge, but without fire. Look to the left of the main conveyor. Another mountain is growing there, a mountain of pure steel. The magnetic belt carries the captured metal beyond the rubber stream, and, where the magnetic field vanishes, dumps it into a separate hopper. You're looking at springs coiled into spirals, long sharp needles, tiny metal chips. Everything gleams under the factory lights with a cold, bluish glow, contrasting sharply against the matte black of the rubber. Stripped of its steel skeleton, the rubber moves forward into the darkest and most airtight section of the plant. Now that the metal's gone, the rubber chunks look surprisingly light, but that's just an illusion before the final battle. We're entering the secondary granulation zone. High-speed granulators transform the torn pieces into perfect rubber crumb. The air here is thick with black snow, fine dust swirling through beams of light. Each granule passes through a system of vibrating screens, where they're sorted by size down to a fraction of an inch. But the real climax lies ahead, inside the sealed steel pyrolysis reactors. We approach the long, insulation-wrapped cylinders. This is the zone of quiet energy. There's no open flame here, but inside, hellish heat reigns, 850 degrees Fahrenheit. The key secret? Total absence of oxygen. The rubber doesn't burn, it distills. There's a metal so rare that humanity mines less of it in an entire year than gold in a single day. A metal that costs $2,000 to $4,000 per pound. A metal you've never heard of, but one that's keeping the plane you flew on for vacation from falling out of the sky right now. This is rhenium, the rarest stable element in Earth's crust, a silvery white metal that doesn't exist as its own ore and is only extracted as a byproduct. Without it, we wouldn't have modern jet engines, and aviation would be stuck at mid-last century levels. Let's dive into the world of the planet's most exclusive mineral, where every gram is worth its weight in gold, and applications are measured not in tons, but in pounds. Let's start with the scale of rarity. Rhenium makes up about 7 ten-thousandths of a part per million in Earth's crust. For comparison, gold is 4 ten-thousandths, platinum is 5 ten-thousandths. But gold and platinum can be found as nuggets or concentrated ores. Rhenium never happens that way. It's scattered as microscopic impurities in other ores, mostly molybdenum and copper. The concentration is so low that even talking about rhenium ore isn't really accurate. It's always ore of something else that just happens to contain rhenium. Rhenium itself looks like a silvery white metal with a slight grayish tint. But most people have never seen pure rhenium. Even in industry, it's often used as alloys or powder. In nature, rhenium occurs in only one mineral, jackasganite, which is so rare it exists in literally just a few places on the planet and has no commercial value. All industrial rhenium is obtained as a byproduct of processing molybdenum concentrates, which themselves are a byproduct of copper mining. It's a byproduct of a byproduct. Imagine the scale. To get 1 kilogram of rhenium, you need to process about 200,000 tons of copper ore. 200,000 tons of rock for a kilogram of metal. It's like looking for a needle, not in a haystack, but in a field planted with hay. The main sources of rhenium are molybdenum mines in Chile, the USA, Kazakhstan, and Armenia. Chile dominates, about 50% of global production. The Chuquicamata mine in the Atacama Desert is one of the largest open-pit mines on the planet, where copper and molybdenum are extracted, with rhenium obtained as a side benefit. The pit is so massive it's visible from space, about 2.8 miles long, 1.9 miles wide, and over half a mile deep. The rhenium extraction process is complex and multi-staged. First, they mine copper ore and concentrate it through flotation, producing copper concentrate. This concentrate contains molybdenum, which is also concentrated and separated. Molybdenum concentrate is molybdenum sulfide with microscopic traces of rhenium, typically from 0.05 to 0.2%. Still with me? Let's keep going. The molybdenum concentrate gets roasted in special furnaces at temperatures around 2000 degrees Fahrenheit or higher in air. Molybdenum oxidizes to molybdenum trioxide, which can then be reduced to metal. But rhenium behaves differently. It oxidizes to rhenium heptoxide, which at this temperature evaporates and escapes with the gases. The gases pass through a complex system of scrubbers, towers where the gases are washed with water or alkaline solutions. Rhenium heptoxide dissolves, forming rhenic acid or perinates. The concentration of rhenium in these solutions is minuscule, grams per ounce, but it's something workable. The solution is purified from impurities of molybdenum, copper, lead, and other metals through multi-stage chemical treatment. Then, rhenium is precipitated as a white crystalline powder. This is the most common form of rhenium feedstock for further processing. To obtain metallic rhenium, the powder is heated in a stream of hydrogen. Hydrogen reduces the rhenium oxide to metal. The result is rhenium powder, which can then be sintered, melted, or used directly. Every year, humanity produces around 50 tons of rhenium. 50 tons! For comparison, we mine roughly 3,000 tons of gold annually and 20 million tons of copper. Rhenium is so rare that global stockpiles at any given moment are measured in hundreds of tons, not thousands or millions. So here's the question: why bother mining something this scarce? The answer: jet engines. Close to 80% of all rhenium goes into the aviation industry to manufacture superalloys used for making turbine blades. A jet engine turbine blade operates in absolute hell. Gas temperatures hit 3,000 degrees. Pressure is massive. The blade spins at tens of thousands of revolutions per minute, experiencing loads of hundreds of tons per square inch. Corrosive environment with sulfur impurities from aviation fuel. And all of this for years of continuous operation with zero margin for error. If a blade cracks mid-flight, the engine disintegrates, the plane goes down. Nickel superalloys. the primary material for turbine blades, contain nickel, chromium, cobalt, tungsten, molybdenum, aluminum, and titanium. But even these complex alloys couldn't withstand temperatures over several thousand degrees for extended periods, until they added rhenium. Rhenium does something remarkable. It dissolves into the nickel matrix of the superalloy and prevents defects from moving through the crystal structure at high temperatures. This is called creep, the gradual deformation of metal under load at temperature. All metals creep, but rhenium slows this process down by several times. Adding just 3% rhenium to a nickel superalloy increases the operating temperature by about 54 degrees Fahrenheit. Doesn't sound like much, but in jet engines, every 18 degrees of additional temperature gives roughly 1% increase in efficiency. And efficiency means fuel consumption, flight range, airline economics. Modern superalloys contain up to 6% rhenium. These are the so-called second and third generation superalloys. A single turbine blade can contain 5 to 20 grams of rhenium. One Boeing 787 or Airbus A350 engine contains roughly 13 pounds of rhenium in its blades. 13 pounds of metal worth $30,000 to $60,000 in a single engine. And a plane has 2 engines. Thousands of jet engines are manufactured every year: passenger, cargo, military. Nearly all the rhenium mined in the world goes right there. Because of its rarity and high price, the industry is desperately trying to cut rhenium consumption. New generations of superalloys are being developed with lower content or using ruthenium, an element from the same group that could theoretically replace rhenium. But ruthenium is even rarer and more expensive, so for now, it's just research. Single crystal blade technology lets manufacturers use rhenium more efficiently. Instead of a polycrystalline structure, the blade is grown as one massive crystal with no grain boundaries, the weak spots. This allows them to reduce rhenium content while maintaining performance. But the process is complex and expensive. Each blade is grown individually in specialized furnaces with extremely slow, controlled cooling. Recycling rhenium from spent blades is critically important. After thousands of hours of operation, blades wear out and get replaced. Old blades aren't thrown away. They're melted down. Rhenium and other valuable metals are extracted and used again. About 30% of rhenium comes from secondary recycling. That's more than most other metals simply because of its enormous value. The remaining 20% of rhenium goes into other applications. Catalysts in petroleum refining, platinum rhenium catalysts for reforming boost gasoline octane ratings, filaments for mass spectrometers and electron microscopes, anode materials for X-ray tubes. Rhenium's strategic importance is massive. Countries without access to rhenium can't manufacture modern jet engines. This isn't just about civilian aviation, it's military too. Fighters, bombers, cruise missiles. The US, with its own molybdenum mines, secures its rhenium supply. Europe and Asia depend on imports, mostly from Chile and the US. China is aggressively ramping up rhenium production, developing their own molybdenum deposits. They get it. Without rhenium, you can't build a competitive aviation industry. Here's the thing. Rhenium was one of the last stable elements ever discovered. German chemists found it back in 1925 while analyzing platinum ore with spectral analysis. They named it after the Rhine, Rhenus in Latin. Before that, Mendeleev had predicted element number 75 would exist, but nobody could find it. It was just too incredibly rare. Right now, you're holding the result of an African tragedy in your hands. Inside your smartphone, laptop, gaming console are tiny components made from a metal mined in the jungles of Congo, where actual wars are fought over it. This is coltan, a dull black rock that looks like an ordinary river stone but costs thousands of dollars per pound, and without which no modern electronics would work. Millions of people have been killed for this rock. Its extraction finances armed groups, destroys guerrilla reserves, and turns people into slaves. But without it, your phone wouldn't exist. Let's peer into the dark world of the most controversial mineral of the digital age, where every like and every post carries the price of a human life. First, the terminology. Coltan isn't an official mineral name. It's short for columbite tantalite. It's an ore containing two metals, niobium, which used to be called columbium, and tantalum. It's tantalum that makes coltan so valuable. It's a silvery gray metal with a unique combination of properties. It doesn't corrode at all, withstands extreme temperatures, has high capacitance, and barely conducts electricity because of a thin oxide film on its surface. That last property revolutionized electronics. Tantalum is used to make capacitors, components that store and discharge electrical charge. Tantalum capacitors are microscopic, the size of a grain of sand, but they have enormous capacitance. They're stable, reliable, work for years without degrading. Every smartphone contains 40 to 50 tantalum capacitors. A laptop, up to 100. Gaming consoles, cameras, even electric toothbrushes. Tantalum's everywhere. Coltan looks like black or dark gray rock with a metallic shine. Heavy, density around 8 grams per cubic centimeter, almost like lead. If you pick up coltan, you feel it's unusually heavy for its size. It occurs as coarse crystals or grainy masses in granite formations. Nothing special to look at, just a rock. But you can get anywhere from $100 to $400 per kilogram, depending on tantalum concentration. The main problem with coltan is geography. About 60% of the world's reserves are in one place. The eastern provinces of the Democratic Republic of Congo, especially Kivu and Ituri. This is one of the most dangerous regions on the planet. For decades, there's been a civil war involving dozens of armed groups that control the mines and use the profits to buy weapons. The story of the coltan rush began at the turn of the millennium. In the early 2000s, demand for tantalum exploded due to a boom in mobile phone and gaming console production. Sony released the PlayStation 2, Nokia and other manufacturers were churning out millions of phones. The price of coltan skyrocketed from $30 to nearly $400 per kilogram. A real gold rush started in Congo, only black. Tens of thousands of people dropped everything and headed into the jungle to dig for coltan. Armed groups seized control of the deposits. Murders, rapes, forced labor began. Kahuzi-Biega National Park, home to mountain gorillas, was overrun by miners. Animals were killed for meat, or simply because they got in the way. The gorilla population plummeted by 90% in just a few years. The UN published a report confirming that coltan sales were financing a conflict that had claimed millions of lives, the bloodiest war since World War II. Armed groups controlled the mines, forcing local populations to work for free or for pennies, smuggling coltan through Rwanda and Uganda, selling it to middlemen who shipped it to China and Europe for processing. Coltan extraction in Congo is mostly artisanal, meaning small scale, no machinery. Miners work in rivers and streams, washing ore in pans like gold prospectors. Coltan's heavier than regular sand and pebbles, so it settles at the bottom of the pan. Or they dig pits in the forest, sometimes 30 feet deep, with no reinforcement. Cave-ins kill people regularly, but nobody keeps track. The working conditions are horrific. People stand waist-deep in murky water all day long, washing tons of rock for just a few pounds of coltan. They make $1 to $5 a day, more than farming, but still poverty. No safety, no rights. Kids work right alongside adults. Women are forced into labor, or worse. Coltan gets collected, dried, and sold to local traders. They haul it to regional centers where Chinese and other foreign companies have warehouses. There, they weigh the coltan, test the tantalum concentration with handheld analyzers, pay cash. Then they ship it out by plane or truck through neighboring countries, Rwanda, Uganda, Burundi, to mask where it came from. Rwanda officially exports hundreds of tons of coltan every year, even though it has almost no deposits on its territory. It's obvious what's happening. It's a transit point for Congolese coltan. The international community knows, but stopping the flow is hard. Borders in the region are porous, corruption thrives, tracing the origin of a specific shipment is nearly impossible. The coltan gets shipped to China, where most of the processing facilities are concentrated. There, it's melted in electric arc furnaces at temperatures exceeding 3,600 degrees Fahrenheit. What comes out is slag containing tantalum and niobium oxides. This slag gets treated with hydrofluoric acid, producing fluorides, which are then reduced to metals through complex chemical processes. Tantalum is incredibly refractory. Its melting point is around 3,000 degrees Celsius, third highest after tungsten and rhenium among all elements. That makes processing energy intensive and complex. Extracted tantalum is converted into powder, which is then pressed, sintered, and turned into anode foils for capacitors just a few micrometers thick. A tantalum capacitor works simply. Thin foil is coated with an even thinner film of tantalum oxide, which acts as the dielectric. Thanks to the microscopic thickness of this film and the massive surface area of the porous structure, you get enormous capacitance in a microscopic volume. This allows electronics to be compact. Without a tantalum capacitors, smartphones would be the size of bricks. Legal coltan mining exists. Australia, Brazil, Canada have deposits and extract coltan using industrial methods that comply with environmental and labor standards. But the cost is higher because you have to pay decent wages, maintain safety standards, and rehabilitate the land. Congolese coltan, extracted through what's essentially slave labor, is cheaper, so demand for it persists. There are also synthetic alternatives. Ceramic capacitors based on barium titanate can replace tantalum capacitors in some applications. They're cheaper and aren't linked to conflict. But for the most compact devices with high reliability requirements, tantalum remains irreplaceable. Military electronics, medical implants, aerospace equipment, they only use tantalum. Tantalum demand holds steady, around 2,000 tons a year. That doesn't sound like much compared to the millions of tons of copper or steel, but given its rarity and concentration in one region, even that amount creates enormous pressure. Every new smartphone, every data center, every 5G cell tower requires tantalum capacitors. Tantalum prices fluctuate between $150 and $300 per kilogram for the metal, or the equivalent for ore depending on concentration. For comparison, gold runs about $60,000 per kilogram. Tantalum's cheaper, but you need way more of it. And extraction is concentrated in a conflict zone, making it strategically critical. The environmental fallout is horrific too. The Congo jungle, one of the planet's largest tropical rainforests after the Amazon, is home to unique species. But artisanal mining is wrecking ecosystems. Forests get chopped down for mines and miner camps. Rivers become polluted with washed-out rock that kills fish and aquatic life. Poaching thrives. Miners hunt wild animals for food. There are attempts to recycle tantalum from electronic waste. Old cell phones, computers, devices contain tantalum capacitors. Technologies exist to extract and recycle them, but economically it's tough. You have to collect massive quantities of old devices, disassemble them, isolate tiny components, remelt everything. Right now, only 5 to 10% of tantalum comes from recycling. Some activists are calling for a boycott of electronics, or at least mindful consumption. Don't swap your smartphone every year. Repair instead of tossing it. Buy used. But here's the reality. Most people don't even know about coltan and the problems tied to it. Manufacturers don't advertise the dark side of their shiny gadgets. There's hope in technological progress. New types of capacitors are being developed that could eventually replace tantalum ones. Graphene supercapacitors promise even higher capacity in smaller sizes. But mass production is years, maybe decades, away. For now, tantalum remains a critical element of the digital age. The irony? Congo is one of the poorest countries in the world, despite its incredible wealth of natural resources. Cobalt, coltan, copper, gold, diamonds, all buried in Congo's soil. But corruption, conflict, and exploitation by foreign companies mean that wealth never reaches the people. It's a classic resource curse. when natural resources become not a blessing, but the cause of endless wars and suffering. There's a metal out there almost nobody ever sees, but it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of % and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces or electric arc furnaces running at temperatures over 2,700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, This is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script, it's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear, it migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxins inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methylmercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest. and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting: cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning. Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it
into its
remains
components.
hottest, settle
The lightest
lubricating
fractions
oils and
collect at
heavy
the top,
residues.
medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change. They simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point, gas oil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gas oil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gas oil has to go through a hydro-treating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture. A process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean? And that every slab of marble is a frozen story of life, death, and time? Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks. Steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price.